How did we get here? As far as we know, it all started with a single thing that expanded in the middle of nowhere. The most common notion of this is an explosion or a boom. Our universe emerged from this boom in a period of time so short that we cannot even imagine. All modern things began at the same time. Particles, hydrogen, space, time, and the four forces of nature. And as a result of this boom, the first stars and galaxies appeared after hundreds of millions of years. But a few billion years have passed and now we are orbiting a planet that inhabits a galaxy. The history of the universe in just 1 minute. This is a very simplified way of talking about the Big Bang Theory, which is a model of how the universe evolved to become what it is today. But I have some information for you if we want to answer the question I asked at the beginning of the video about where we came from. The Big Bang Theory is the scientific community's preferred model for finding an answer to this question. Furthermore, the reason behind its popularity is simple. The observations are in line with theoretical models that were predicted by the Big Bang. However, what appears to be a simple and easy situation is not true. Cosmology is an area of science that seeks to understand how the universe began and evolved, using models and observations. Cosmology, on the other hand, faces a rather complicated problem. We can study only one universe. In science, to prove a model, we have to make observations. These observations are made by doing experiments or observing repeating phenomena. The situation is more complicated in cosmology, as it is impossible to build a universe in the laboratory to test each cosmological model. Furthermore, we do not have the ability to examine the other universe to determine if any changes occur among us. Therefore, cosmology is based on past observations of our unique universe. This means that it is necessary to make observations of our universe at various stages, from childhood to adulthood. And for that, we need better and better data. Chronology details will be obtained from the moment of the Big Bang. And this can only be done with sophisticated technologies, such as increasingly sensitive telescopes that can reach increasingly distant locations, billions of light-years away. Due to the fact that it is a measure of distance, the light-year gives us a sense of time at the same time. When we say something is billions of years away, it also means that the light we are seeing is light that was released billions of years ago. The reason we need more powerful telescopes is because they allow us to see further, which allows us to see better into the past. The construction and launch of the Hubble telescope in the 90s also serves as an example. To estimate the expansion rate of the universe, the Hubble telescope was mainly used to observe more distant regions. Some of the most stunning photographs in human history were created by the Hubble Space Telescope. However, cosmology has only managed to advance in the last decade. Using the James Webb Space Telescope. The James Webb was designed as an innovative telescope aimed at answering questions like when did the first stars appear? How did galaxies develop? How did supermassive black holes appear? Furthermore, to achieve this goal, James Webb would have to examine a past of the universe that had never before been explored. And I'm referring to something that occurred just a few 100 million years after the initial explosion. And I really understand that you might be thinking that this is still a long period of time, and just using the word millions of years seems to be a mistake. It is important to remember that we are talking about the universe. Furthermore, its estimated age is 13.7 billion years. When it comes to the universe, hundreds of millions of years are just the blink of an eye. Furthermore, there is an additional reason why researchers are interested in this period. Within cosmology, this period coincides exactly with the time when we assume the first galaxies and stars emerged. So from the beginning, James Webb's concept aroused enthusiasm, specifically to answer these questions. Furthermore, during the last years of his native life, James Webb already discovered several discoveries. And one of these results occurred right in the initial observations, in July 2022. In particular, the first deep-field image taken by James Webb. In the first image, some astronomers noticed a problem. Something our theory did not expect. The galaxies were much larger than we expected. This presents a problem, because in the most popular model of galaxy evolution, there would not be time for galaxies to reach those sizes. As a result, many people quickly began to question the Big Bang theory, while astronomers were left with doubts. Considering that the universe was young, it must be much older than we thought if the galaxies didn't have time to get that big. The Big Bang theory must be wrong soon. And that was basically the idea that many people came up with that ended up going viral on the internet. To this day, it is common for people to claim that James Webb proved that the Big Bang did not occur. But was that really what happened? Did James Webb manage to prove that the Big Bang did not occur? Or is there a better explanation that actually helped astronomers solve their problem? It's a spoiler. Although it's not the way you're thinking now, it's possible that some things in astronomy will change completely. In fact, a mathematical model known as Lambda CDM is connected to the Big Bang theory. The following translation of Lambda CDM is possible. The Greek letter lambda is a representation of the cosmological constant. In Portuguese, cold dark matter, or dark matter, is abbreviated as CDM. A factor related to the expansion of the universe is the cosmological constant. Furthermore, it is important to keep in mind that dark energy is related to the expansion of the universe. Therefore, the study of dark energy is often associated with the calculation of the cosmological constant. Einstein's equations of general relativity include the constant. And the behavior of spacetime, including its expansion, is explained by these equations. And I am aware that when we discuss these equations, we talk about black holes, a distortion of spacetime. However, the importance of these equations goes far beyond describing the universe. These equations have some parameters, including the cosmological constant. Albert Einstein first introduced it to counterbalance the effect of gravity on equations. However, a few years later he abandoned the idea, thinking that the constant was wrong and there would be no point in putting it there. Furthermore, at the end of the last century, evidence emerged that shows that the universe is not only expanding, but also expanding at an accelerated rate. And a repulsive effect, which is the opposite of gravity, would cause this acceleration. When Einstein used the cosmological constant at the beginning of the last century, he thought the same way. Astronomers added the constant to the equations with this. This led to the joke that Einstein always gets it right, even when he gets it wrong. The term cold dark matter in the name also refers to dark matter. Dark matter in this model is non-collisional and has low speeds. Alternatively, something cold if you prefer a more physical approach. The Lambda CDM model has already predicted a variety of outcomes. The amount of elements such as hydrogen and helium, the acceleration of the expansion of the universe and the cosmic microwave background radiation are some examples. Furthermore, this model has already predicted the distribution of galaxies in the universe, a phenomenon known as large-scale structure. Therefore, astronomers and cosmologists prefer Lambda CDM. He has experience in making successful predictions and is always tested with deeper and deeper observations. As a result, the Lambda CDM model is preferred for explaining the origin and evolution of the universe. But what kind of change does the model predict? Let's suppose I showed you a balloon that is already a little inflated and I keep inflating it every minute. You see how it expands, and if you think about its past, you assume that at some point in the past it was empty. To reach this conclusion, you don't even need to have seen it empty. When you see how it expands and fills, you automatically rewind it in your head and come to that conclusion. The universe would be like a balloon for the Lambda CDM. Since we know that the universe was smaller in the past, we can assume that it was so small at one point. However, it was so small that it was just a single occurrence. A place in the middle of nowhere. The current expansion began at this point. This is the famous explosion known as the Big Bang. The universe was hot enough to form plasma in those early moments after the Big Bang. Plasma is a state of matter in which temperatures are high enough to cause components to be ionized. Although few know, the universe underwent two accelerations. Inflation was the first of them. In inflation, the universe went from the size of an orange to the size of a galaxy in 10 seconds or so and 33 seconds or so. If you were observing the universe at that time, you wouldn't know when it stopped being the size of an orange and became the size of a galaxy. For you, this would have been instantaneous. This represents the level of inflation. Furthermore, the universe continued to expand after inflation, which caused it to cool down and lose temperatures so high as to cause the elements to be ionized. Atoms formed this way from the first few minutes to the first 300,000 years. Neutral hydrogen was first formed, followed by helium atoms. This also marked the beginning of the formation of the first molecules composed mainly of hydrogen and/or helium, such as molecular hydrogen. After 300 to 400,000 years, we entered the Dark Ages. There was no exact light. As most elements and molecules were already in their neutral form, there was no phenomenon that produced photons. The universe had no light. But by the time it reached its first few million years, we would expect stars to have begun to form. They would form when cold clouds of molecular hydrogen collapsed. Furthermore, these stars would be the first source of light that the universe would see for a long period of time. And then larger structures, like galaxies, began to form. The age of stars begins at the end of the Dark Ages, about 1 billion years after the Big Bang. It is in this era that the universe we live in today begins. The name suggests that it is an era dominated by star formation. I would like to go back a little more to this story, however, because we are focused on the Dark Ages. It is imperative that I recognize that some observations agree with the explanation I have just given of the evolution of the universe. Furthermore, Lambda CDM incorporates the mathematical model. However, the Dark Ages may be the main source of problems in this location. The first problem arises because we are talking about the universe in a very ancient era in which we did not have enough technology to observe. Due to the fact that many of the still open questions regarding astronomy are strongly influenced by the events that occurred at that time, the second problem arises. They include the formation of the first stars and the emergence of the first galaxies. Astronomy still does not know how a galaxy forms. Several models tried to explain how it happened, but none of them managed to solve the problem due to a lack of observations. They formed as a result of a hierarchical model that involved smaller structures coming together to form the galaxy, or they may do so through a monolithic model, in which the galaxy formed only once shortly after the collapse of a cloud of grotesque gas. It's possible that the supermassive black hole pulled in matter and formed small blocks of stars, or that the galaxy had already been formed before the black hole was pushed there by an uncertain gravitational push. This is like an astronomical version of the question of which came first, the chicken or the egg. Did the black hole or the galaxy arrive first? This era was observed using the Hubble telescope. But Hubble saw ancient galaxies that were small and not very massive. The hierarchical model of galaxy formation was most compatible with these galaxies. However, Hubble was not a telescope designed to observe extremely distant areas. It wasn't built for that. Therefore, it was not possible to determine whether what they were observing actually showed that the hierarchical model was correct. As a result, a new telescope with enough technology to see as far as possible was needed in order to observe the first galaxies and stars. This would finally put an end to the discussion of how galaxies formed. This was the starting point for the concept of the James Webb Space Telescope. The James Webb Space Telescope, also known as the James Webb Space Telescope, is designed to replace the Hubble telescope. It is important to make it clear that they differ from each other and have different objectives. Therefore, this expression is incorrect. The first difference is that James Webb's observation is carried out at infrared wavelengths. Only a small area of the infrared is observed by Hubble in the optical. Another difference is that James Webb was designed to observe the first light in the universe, which occurred in the Dark Ages, approximately 100 to 400 million years after the Big Bang. Hubble's goal was to calculate the expansion rate of the universe by observing various epochs of our universe. The James Webb telescope has about 6 times the light-catching area of the Hubble telescope. This increases its sensitivity and quality. As more photons are captured, more information about objects is captured. However, the biggest factor that certainly makes a difference is the range of light that James Webb observes. Additionally, this range allows you to see even further than any currently available oscilloscope. To be more precise, James Webb observes at wavelengths ranging from 600 to 28,500 nanometers. Furthermore, these lengths fall into the area of the spectrum known as infrared. You may wonder, why observe in infrared? Why not in optical or even ultraviolet energy lengths? Which would make sense if we consider that we are talking about things that release a significant amount of energy. The Doppler effect explains this. This is the same thing that causes an ambulance's frequency to change depending on how fast it approaches and moves away. The cosmological Doppler effect is also seen in the cosmos. When a remote galaxy or star releases photons, they will move through the fabric of spacetime until something absorbs them. The photon's wavelength is stretched together as the universe expands. Imagine the photon as a spring. The spring is stretched along with spacetime as it moves. This is like pulling an elastic spring. Furthermore, this effect causes this photon to stretch, emitting a longer wavelength. The cosmological Doppler effect increases the distance from the source to us. And using this equation, we can even calculate the distance at which the photon was released. Z, known as redshift, measures length extension. Additionally, it makes it easier to find the source. In the case of these first galaxies, the photons traveled for a suitable period of time. To focus on infrared wavelengths. This also justifies the need to use infrared observation tools. The season cannot be seen without this. Furthermore, because we are talking about extremely distant objects, we need sensitive tools. Therefore, only a small number of photons reach us. Furthermore, the ability to observe at these wavelengths and its larger collecting area are a major revolution in the James Webb compared to other telescopes. In my opinion, the launch of the James Webb Ariane 5 rocket on December 25, 2021 was probably the most significant event in the history of astronomy this century. James Webb had already recorded the first images, which were released in July 2022, 6 months after launch. In total, NASA released 4 photos and a spectrum in a live broadcast. On July 12. However, the day before, the White House had released the latest deep-field image of the James Webb. It didn't take long for astronomers to look at the first images to do an in-depth analysis of them, and they soon found galaxies that broke the record for the most distant objects that had ever been seen. In the first image, one of several articles published called "Panic at the Disks." I think I know what the author's favorite type of music is, because he was one of the first to do it and even discovered some of these galaxies. Although other authors and groups reached similar conclusions, a problem soon emerged. They calculated the masses of these galaxies and found that they were much larger and more massive than theory predicted. Furthermore, their structures were more complex than expected. Galaxies so young that they theoretically had not yet formed. They were already like much older galaxies in terms of size, mass, and structure. Like the impression left by Hubble, they should be small, not very massive and unstructured. The problem is that because small structures formed slowly over billions of years, this could mean they were already large when the universe was so young. These unstable structures did not form until the universe was a billion years old. In short, according to what we know about the evolution of galaxies, galaxies were much more advanced. It is impossible for them to have formed in just a few million years. The controversy began when astronomers discovered that something was wrong. At that time, astrophysicist Alison Kirkpatrick from the University of Kansas was invited by Nature magazine to talk about the discoveries made by James Webb. Furthermore, astrophysics experts have used the following expression to refer to these discoveries in the context of this subject. I'm up at 3 in the morning now and I'm wondering if all the work I've ever done was done wrong. This caused some people to take this phrase and use it to say that the Big Bang wasn't true. This quickly spread across the internet, and the headlines were James Webb demonstrates that the Big Bang never happened. And the argument that all these articles use is that the universe did not have a disk when these galaxies existed. For them, the Big Bang could not have happened because the universe was older than they imagined. Plus, this has become so popular on the internet that you can still see people using this argument. When someone mentions the Big Bang, however, is that really what happened? Has James Webb demonstrated that the Big Bang theory, as well as all current theories about the evolution of the universe, are incorrect? Kirkpatrick came forward publicly to claim that the sentence she published in Nature magazine had nothing to do with the Big Bang. She changed her name on social media saying that the Big Bang theory was the best explanation for the origin of the universe. So, what is the reason behind her phrase and where does all this confusion come from? In fact, it is true that galaxies exceed the size predicted by theory. Thus, theories will need to be revised. However, it is not the Big Bang theory. You may have noticed if you watched the video that James Webb was presented with a series of open-ended questions. One of them concerns the formation of galaxies. No available telescope had the ability to capture the universe's remote past before the appearance of James Webb. The brief observations. The specimens that were found in Hubble were of low quality and, therefore, it was impossible to say anything about them. Technology prior to James Webb made it impossible to confirm one of the theories of galaxy formation. Thus, this question was one of the tasks that James Webb had to solve. I think if it was built and launched with billions of dollars invested, that's because the issue remained open and needed to be resolved. A question that already had an answer wouldn't make much sense. Furthermore, James Webb discovered that our concept of galaxy formation was incorrect. I want you to pay attention to the following point. Astronomy has always kept the question of galaxy formation open. This was not done by James Webb. The fact that James Webb demonstrated that our assumptions were incorrect only leads us to consider galaxy formation models again. Furthermore, this is what astrophysicist Kirkpatrick intended to say when addressing all the. She discovered she had made a mistake. For astronomers, who have always had doubts about the galaxy formation model, this isn't even that surprising. With these observations, James Webb demonstrated that these models need to be rethought. Science has always done this. Observations are used to test a model. We redo the model if the observation doesn't work. This is nothing new, science has seen this before and will continue to do so. This represents the beauty of the scientific process. Basically, we had something called galaxy formation, which we only had a vague idea of how it worked. After that, James Webb arrived and revealed that our expectations were not correct. The Big Bang theory also doesn't work if the theory of galaxy formation is wrong. Could it be? Furthermore, you are absolutely right to say yes, as our discussion is about science. I'm very happy that you asked yourself this question, because statements should be questioned. Additionally, I want to introduce you to another fascinating facet of science, why some models are more popular than others. To begin with, the Big Bang model is the one that most agrees with the information we have, but that doesn't mean that the hammer has definitively fallen. The only thing is that so far, no model has been able to explain these observations better than the Big Bang. However, there is not enough evidence to say that the Big Bang did not occur. Furthermore, we enter that famous phrase by Carl Sagan. Extraordinary arguments require extraordinary evidence. Therefore, we need evidence to confirm the extraordinary claim that the Big Bang did or did not happen. The evidence is not enough. We need to have several that have been tested multiple times by multiple groups using multiple approaches. And that's exactly where the claim that the Big Bang happened comes in. She has made many observations with various groups over the years, using various approaches that have been revised. All of these things combine to make the Big Bang theory the best explanation for how the universe began. The cosmic microwave background radiation, which is predicted by the Lambda CDM model, is the main focus of these observations. Additionally, the perturbations and temperatures that the model predicted are also additional observations. This statement is also corroborated by the observations made by telescopes such as Hubble, as well as others that can map large-scale structures. All the different ways of calculating the expansion rate of the universe agree on the mathematical model that explains the Big Bang. Therefore, the Big Bang coincides with a collection of observations from various perspectives that have been repeated many times. James Webb's focus is observed infrared. It would not be enough to refute all these other observations even if it had proven otherwise. However, it is essential to make one thing very clear. Nothing has been demonstrated against the Big Bang by the data collected by James Webb. They just proved something wrong against the idea that we had of galaxy formation. And of course there are claims and experiments that try to show that the Big Bang model is wrong. However, these experiments do not provide enough evidence to support the thesis that the Big Bang was not true. There is little evidence that the Hubble images were not of high quality, given our own theory of galaxy formation. The galaxy formation model has less evidence than the Big Bang model. Furthermore, I believe this serves as an excellent example of how science works and how lies spread easily across the internet. For the first time in history, James Webb offers us a more detailed view of the young universe. It will not only help us build models of things we never imagined existed, but it will also answer questions that still have no answers. That's what he did. He gave us information about something we never knew exactly how it worked because we had little information. Our mother taught us the same lesson here. Always look for reliable references and don't trust everything you read on the internet. For example, these videos are always in the description, just like all other Science Daily videos. Furthermore, it is useful to learn about the nature of science and that theories are not just concepts with meaning common to everyday use. Within science, theory is important because experimental data has proven its veracity. When you read that someone has disproved a scientific theory or concept, remember this. However, I believe the lesson Carl Sagan taught in this video is the most significant. Extraordinary arguments require extraordinary evidence. My gratitude, and until next time.